Hi everyone. So in this video, we're going to be talking about a new method for evaluating indefinite integrals. So as I mentioned in the last video, so far when we've been finding antiderivatives, they've all been fairly simple antiderivatives, right? They've been ones that you can just figure out either using the reverse power rule or just by kind of recognizing, oh, I know that this function is the derivative of some other function. But as I mentioned, as this course moves on, we're going to be looking at a lot of examples of trickier antiderivatives, and we're going to need like methods for finding those antiderivatives. They're not always going to be ones that you can just kind of look at and recognize. So one of the most important methods that we'll have in order to evaluate more complicated antiderivatives is something that's called substitution. So in this video, we're going to be focusing on substitution for indefinite integrals. So just to remind you, an indefinite integral is an integral where there's no a or b, right? It's just like integral of f of x dx. And basically it just means find the most general antiderivative. So it's just a symbol for antiderivative. Whereas a definite integral, that does have an a and a b, and that refers to a number, right? You have to actually calculate a number using the fundamental theorem of calculus part 2. And so in the next video, we'll focus on how this substitution method works for definite integrals, because it does have kind of one other thing that you have to keep in mind. So I want to start off with a kind of a warm-up example of just calculating a couple of derivatives real quick, because we'll see that substitution is basically, it's almost like the backwards of the chain rule. And so I want to just make sure that you remember how the chain rule works. So these are both pretty simple examples, but find the derivatives of the following functions. So first one is f of x is equal to e to the 2x. And then the second one is g of x is equal to cosine of x cubed. So take a moment, think about if you know what these answers are, or pause the video if you want to kind of write it down and find the answers. Okay, so what goes on with this first one? Well, how does the chain rule work? Basically, there's this kind of outside part of the derivative and inside part of the derivative. So when you have a function that's e to a power, the outside part of the derivative is e to a power. And so what is the derivative of, e to the x or e to the u or e to anything? Well, it's just e to that thing. So the first part of the derivative is just e to the 2x. That's the outside derivative. But then we still need to multiply by the derivative of the inside function. So the inside function in this case is 2x. And so the derivative of 2x is 2. And so we get 2e to the 2x. And then in this case, our outer function is cosine, right? So what's the derivative of cosine? It's negative sine. And so then we have negative sine of x cubed. And then we have to multiply that by the derivative of our inside function, which in this case is x cubed. So that gives us negative 3x squared times sine of x cubed. So if you're at all rusty with the chain rule, you just don't remember how it really works, if you go look at my videos, you might have to go back a little bit from last quarter. You'll see that I have a 151 video, a Calc 1 video that covers the chain rule, at least one. I probably have a few about the chain rule, so you can go check those out. So I want to point out one kind of difference between these two, because this is something we'll see come up when we get into our integration method, which is that in this case, notice that our derivative, so that the chain rule didn't give us an extra x, it just gave us an extra number, right? And the reason that happened is because if we look at this function as a composite function, our inside function was only a constant times x, right? And we would have the same situation if it was e to the 3x or e to the 5x or e to the negative x or anything like that. Anytime it's just e to just a multiple of x, your derivative is just going to differ by this multiple of whatever, that same number. So if we have 2 times x, we end up with 2 times e to the x. Whereas in this example, because the inside function, it wasn't just 2x or 3x or something like that, in which case it would have looked, the derivative would have come out more like the one on the left. In this case, our inside function is actually x cubed, and so its derivative is a little bit more complicated, and it actually brings in a new x. So I just want to kind of point out that difference, because we'll see that same kind of difference come up in these integrals. So I want to start with a simple example. And so this is an example that I think I probably gave you this example on a worksheet at the beginning of the quarter, or I at least gave you something similar. So this is an example that you can do just kind of using this like guess and check idea, or basically by looking at what's going on. Sorry about that. Looking at what's going on with this derivative, you can kind of just work backwards and figure out what the answer is for the antiderivative. So we'll do that first, just to kind of see like, how could you figure this out? You know, just kind of thinking through it and maybe using some guess and check. But then we'll see that there's a more official method called substitution that will kind of, if you're someone who doesn't really like guess and check, you don't like to feel like there's uncertainty, you know, I think that you will like this substitution method. That being said, as we go through the video, we'll see that there are examples where substitution is even more important to use. So there will be some examples in this video where there's multiple ways to do it. You know, you don't have to use substitution, but we'll eventually see some examples where substitution is really kind of the only way to get your answer. So yeah, so how would you do this kind of with this guess and check, or just sort of thinking through it idea? Well, you know, if you had to guess, what do you think the antiderivative of e to the 2x is, you might guess e to the 2x, right? Because that's just kind of how e to the x works. So you would think, oh, well, wouldn't it just kind of be the same function? And so why am I calling this guess and check? Well, the nice thing about antiderivatives, and this is so important, is that anytime you're taking an antiderivative, and I guess I should say plus c here, anytime you're taking an antiderivative, you can always check whether it's right, because you can just take the derivative and see whether you get the function you started with. So I think this is something that students tend to, not want to take the time to do, but, definitely on like a test or something, I recommend checking it by taking the derivative. But I also think that taking the derivative in order to check your work not only will just help you see if you got the right answer, but I think it will really help you understand if you got the wrong answer, why it's wrong. Like, it will help you kind of see where different parts of the function are kind of coming into play. So I really, really recommend, and I'll mention that again throughout this video, but checking your answers when you're finding antiderivatives. So how could you check this? Well, if you take the derivative of e to the 2x, we actually just did that one above, right? So we know that the derivative of e to the 2x is actually 2e to the 2x. And so that's not quite right. That's not, we started with just e to the 2x. So how would we need to change our answer for the antiderivative in order to get the right thing when you take the derivative? Well, we need to get rid of this 2, right? When we took the derivative, we ended up with this 2, whereas there's no 2 here. The coefficient is 1. And so what we can do is introduce a factor of 1/2, right? So if we instead, this is now our second try, say, okay, let's now try, maybe the antiderivative is going to be 1/2 e to the 2x plus c. And let's see whether that works. So now when we take the derivative, oops, sorry, I forgot the 1/2. So now what happens when we take the derivative? Well, now we have 1/2 times 2e to the 2x plus c, right? Because we know that the derivative of e to the 2x is 2e to the 2x, and now when we multiply it with 1/2, now that simplifies just to e to the 2x. And I don't know why I wrote a plus c here, sorry. And so this is the correct answer. So we just figured out that the antiderivative of e to the 2x is 1/2 e to the 2x plus c. So that's kind of the guess and check method. Totally works well on this example. But I now want to show you this method called substitution. So the way that substitution is going to work is that we're basically going to, you basically are looking for kind of what's the inside function within your integral, and you're going to substitute it out to just be another variable. And basically what will happen is you'll be left with a more simple integral that you can actually just evaluate using your, easy antiderivative rules. Okay, so let's see how that plays out. So our function that we're trying to integrate, we have e to the, and I'm going to just use a different color here to emphasize what's going on, e to the 2x, and then I'm also going to use a different color for dx, and we'll see why. So the substitution we're going to make is we're going to let, and typically you use the letter U for substitution. You can use a different letter if you want. You could use Y, you could use W. Basically you're just choosing a different variable that's, a variable that's different from the one that you started with. So let's let U equal 2x. So basically we're going to be changing this, this 2x to a U. And so if we just did that, so if we only changed the 2x, we would be left with e to the u dx. But there's a problem with this, which is that we've talked about this in this class, that you want the variable in your integrand to match the variable that is attached to the d, dx, dw, du, whatever. You need it to be the same variable as in your integrand. And so what we need to do is we need to also find a way to change dx into du. And so the way that we do that is that you take this statement. So here we said u is equal to 2x. We actually take the derivative of both sides. So if you were to take the derivative of both sides of this statement here, you would get du dx, and sorry, take the derivative with respect to x. So du dx is equal to 2, right? That's the derivative of 2x. It's kind of like if you had a y here, right? Y is equal to 2x, then you would say dy dx is equal to 2. It's the same idea, just with a u. And so if we move this dx to both sides, we then have du is equal to 2 times dx. And then because we're trying to get rid of this dx, right, this is what we're trying to kind of translate into u, we want to take this equation here and solve it for dx. So if we divide both sides by 2, we find that du over 2 is equal to dx. So we're now going to go into this integral and we're going to replace, so now we have e to the u, but now we can replace this dx with du over 2. And so a nicer way to write that would be taking this over 2 and taking it outside of the integral. So we're left with 1/2 times the integral of e to the u du. Okay, so now we're left with a simpler integral, right? We're just like, this is the same as if you were integrating e to the x dx, right? So you can now kind of forget about what your original function was and just focus on this integral. Think of this as a brand new integral, forget about what u represents, and just take the antiderivative. So what's the antiderivative of e to the u? Well, it's just e to the u, right? So we have 1/2 e to the u plus c. And then the last step we need to do is we have to reintroduce our original variable, right? Because we were not asked, like when we were originally handed this antiderivative question, we had a variable of x. And so we need to put it back in terms of that variable. And so all you have to do is go back to this kind of key you created for yourself and replace u with 2x. And that's it. And notice we got the exact same answer that we got earlier. And personally, for an example like this, so for an example like e to the 2x, I personally prefer this example, or this kind of method above, of just kind of intuitively thinking about it, thinking about what's that extra factor going to be when I take the derivative and kind of figuring out how to counteract that. But I found that a lot of students prefer to do it this way just because it's a little more methodical. But like I said, so in this video, basically we're just going to do a lot of examples and we'll see all the different ways, or I shouldn't say all the different ways, but a lot of the different ways that substitution can play out. So again, you might see this example and think, this is a lot of work for something that you might have been able to do like in your head, but we will see some examples where substitution becomes really important. So, I'm hoping this video won't be too long. I know the last couple have been on the longer side, but if it is, it's just because we're just going to do a lot of examples. So, you can feel free if you feel like you totally get it, you can stop because I'm just going to go through more and more examples. But like I said, the different examples I think are going to bring up some different kind of things. And I also would really, really recommend, I know I say this every time, but it's going to be really important that you take a look at the worksheet for today, because even though I'm going to do a lot of examples in this video, there's no way I can cover every single possible variation of substitution, and there are just a lot of different ways it can show up. So I think the most important thing you can do with kind of integration problems in general, just because like there are just so many different types, is practice. Practice is going to be very, very important in this class. So let's jump into some more examples. Okay, so the next example I want to look at is we're going to take the integral of 2x times the square root of 1 plus x squared dx. So this example kind of has something in common with this first derivative we did. So I'm going to go back here for a second. So notice that in this second part, so over here, let's say I had asked you to find the antiderivative of negative 3x squared times sine of x cubed. Well, we know because we just did it that the answer would be cosine of x cubed. But how could you kind of recognize that there's some chain rule going on here? Well, notice that the derivative of the inside function appears in your integrand. And so that's going to be a major clue for when substitution is an appropriate method to use, is when you see kind of a more complicated input, something that's not just x, but then additionally, you actually see the derivative of that complicated input in your integrand. And so that's exactly what's going to be happening in this example. So notice that we have the square root of 1 plus x squared. We don't know how to take the antiderivative of that. We do know how to take the antiderivative of just square root of u, right? Or square root of x. So basically, if we can take this input and just turn it into u, we will know how to take the antiderivative. Additionally, notice that the derivative of this input, so the derivative of 1 plus x squared, is 2x. And so that's really a hint when you see a situation like that where you have this more complicated input, and then additionally you see the derivative of that input, that should signal to you, okay, this is going to be a substitution problem. So I want to rewrite this again kind of the way that I did the last one, just to really emphasize the parts of the function here. So the things that we need to switch over to u, well, we're going to have this 1 plus x squared, that we need to change into being something in terms of u. And then we also have this dx that needs to change into being something in terms of u. So the first thing we're going to do is we're going to let u equal 1 plus x squared. But like we saw in the last example, we also need to find a way to change the dx into a du. And then you might also be wondering about this part. We'll see that when we do the dx du business, that will kind of take care of that 2x, and we'll see how that happens. Okay, so if we take the derivative of this equation right here, we have du dx is equal to, so the derivative of 1 plus x squared would be 2x. So if we multiply both sides by dx, And a lot of people, by the way, will just kind of jump to this step rather than writing. I like to say du dx just to really kind of show you where this next step comes from, but you can feel free to go straight from here to here once you kind of recognize how it works. So we have du is equal to 2x dx. So we want to solve this for dx so that we can know what to put in for dx. So if we divide both sides by 2x, we get du over 2x is equal to dx. So now we're ready to do our substitution. So we get the integral of, and so we still have this 2x in here. Now we have the square root of u, and then we have du over 2x. So this this 2x cancels with this 2x. And we're left with just the integral of the square root of u du. And that's great. Now we can forget about the x's and just kind of focus on this much more simple integral. So how would you evaluate the antiderivative of this? Well, you would probably want to rewrite it as u to the 1/2. And then you just use the power rule. So the antiderivative of u to the 1/2 would give you a new exponent of 3/2, right? Because you're adding 1 to the original exponent, and then you have to take the reciprocal of that, right? So it's u to the 3/2, and then the reciprocal of that is 2/3. And then we want plus c. So now we go in and we change it back to our original variable. So we take this u and we replace it with what we substituted u for. So u was equal to 1 plus x squared. So we're just going to put back in 1 plus x squared here to the 3/2 plus c. So let's check our answer real quick. And then I also want to put it into kind of a nicer format just to kind of see what would be maybe a slightly better way of writing your answer. But while it's written in this form, it's going to be easier to take the take the derivative. So how do we check this? We just want to take the derivative of what we just found, and we want to then see whether it gives us our original integrand. So we're taking, I'll use this notation. So 1 plus x squared to the 3/2 plus c, we're taking the derivative. So that notation means derivative of. So how would you take the derivative of this? Well, you'd have to use the chain rule, right? And so the outer part of the derivative would involve taking this exponent and bringing it down and multiplying it with the original coefficient. So we would get 2/3 times 3/2 times 1 plus x squared. And then the new exponent would be 1/2, right? Because you would subtract 1 from the exponent when you're taking the derivative. But then you have to multiply by the derivative of the inside function, right? Because this is a chain rule derivative. And so the derivative of the inside function would be 2x. And so altogether, the 2/3 and the 3/2 cancel out, and you would be left with 1 plus x squared to the 1/2, which is the same as the square root of all that, times 2x. And maybe I'll rewrite it this way, just so it really matches with what we started with. So 2x times the square root of 1 plus x squared. And if we look back at our integrand, we'll see that that is exactly what we were supposed to be taking the antiderivative of. So yeah, let me rewrite this rewrite our answer in a slightly nicer way. So our answer we originally wrote like this. I think a slightly nicer way to write this would be to put the, instead of writing it as 1 plus x squared to the 3/2, you could write it as the square root of 1 plus x squared cubed. And then put the 2 and the 2/3 kind of like that, and then say plus c. And that would be our final answer. Okay, so more examples. So let's see. As our next example, let's do, and I would encourage you as I'm going through these, as soon as I tell you the question, you could pause the video and, try it yourself. So let's try this one. The integral of e to the x plus 10 dx. So we'll see that this one is actually one where, again, you don't really have to use U-substitution, but it works to use U-substitution. So I want to kind of show you how it plays out. So how would you kind of rewrite this in order to figure out what's going on? Well, we know that the x plus 10 would be the thing we would want to substitute out, right? Because that's our more complicated input. And then we know that we also want to get rid of the dx. So what we'd want to do here is we'd let u equal x plus 10. And then du dx would just be equal to 1, right? The derivative of x plus 10 is just 1. And so that would tell us that du actually is just equal to dx. So when we go in and do that substitution, we would get the integral of e to the u du, which we know is just equal to e to the u plus c. And then we would go and put back in our original input, so e to the x plus 10 plus c. So why am I saying you don't really have to use U-substitution here? Well, one thing that might be convenient to realize is that anytime you have an input that is just x plus or minus something, when if you were to use the chain rule, the inside part of the derivative would just be 1, right? So same thing if you had like sine of x plus 1 or square root of x minus 3 or anything where your input is just x plus or minus a number, you do have to use the chain rule to take that derivative, but the inside derivative is just going to be 1. And so you could basically just recognize from this, okay, the antiderivative of e to the x plus 10 is just e to the x plus 10 plus c. All right, let's do another one. So next up we have the integral of x cubed times cosine of x to the 4th plus 2. So again, let me just kind of highlight some different things here. So in this case, this is one where we have kind of an extra x thing floating around, and we're going to hope that that cancels out when we do our substitution. But we can see that we have this input of x to the 4th plus 2 that it would be nice to be able to get rid of. And then we have our dx. So if we set u equal to x to the 4th plus 2, then we get du dx is equal to just 4x cubed. So now if we multiply both sides by dx, we have 4x cubed dx. And so that tells us that du over 4x cubed is equal to dx. So basically what's going to happen when we do the substitution is that x cubed is going to cancel out, but we'll be left with an extra factor of 1/4, which is okay. That, if you're basically, if there's any extra x's in, or whatever your variable is in your function, that's going to be a situation where, that really needs to cancel out. But if you're left with just some extra number on its own, that's okay, because then you can pull, if it's a constant, you can pull it out of the integral. Whereas if it's x cubed, you can't. You have to really be able to deal with it within the integral. So we can rewrite this as x cubed times cosine of u. And then we can replace, we can replace dx with du over 4x cubed. And so now we see that this x cubed and this x cubed cancel out, and so we're left with the integral of cosine of u du. Okay, so what's the antiderivative of cosine? Well, it's just sine, right? So our answer here would be sine of u plus c. And then our last step is just to, and sorry, I missed something, my bad. So what did I miss? I missed this 1/4, right? I forgot about that. So usually what I like to do is when you have an extra kind of multiple or something you're dividing by, just pull it completely outside of the integral. That way you don't really have to worry about it. You can just focus on what's on the inside of the integral. So we're left with now 1/4 sine of u plus c. And then our last step is to return that to our original variable. So we want to replace the u with x squared plus 4, or sorry, x to the 4th plus 2. And I'll just rewrite it as x to the 4th plus 2 over 4 like this, plus c. And again, for the sake of time, I'm not going to, for the rest of them, I'm not going to go through and check the answer, but I really encourage that you do, especially if you feel like you're still, not totally confident with how these work. Okay, so I'm going to now, the next few examples we'll look at are going to be a little bit trickier or have some other kind of trick to them. So let's start with this next one. So let's start with the integral of tangent of x dx. So this is one that was actually on that that antiderivative table I shared in the last video, but I think it's interesting to be able to see where that antiderivative comes from. Because if you think about it, if you think of all of the different trig derivatives we don't know off the top of our heads anyway, a trig function whose derivative is tangent, right? We know like the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared. There is no trig function whose derivative is just tangent. So this on the surface might not seem like a substitution problem, but we can rewrite it in a way where it becomes one. So let's rewrite tangent of x as sine of x over cosine of x. So why is this helpful? Well, now we can notice that the derivative of, like, sine and cosine are derivatives of each other. And so basically that kind of hints that we should be able to do some kind of a substitution here. So the correct substitution to make here is we're going to let u equal cosine of x. And the reason that the correct thing to do is to let u equal cosine and not sine is because the way that cosine appears in this function, it's 1 over cosine. So if we let u equal sine of x, we wouldn't have the correct derivative appearing in our result. That being said, if you were to try it with like letting u equal sine, that's great. I think like I said, guess and check is like the best thing you can do in this class, and you are going to have to do it. Like there's going to be examples as we move throughout this quarter that are going to get more and more challenging, and you really are going to have to get comfortable with this idea of trying something and it might not work, and that's okay. It's okay to not get something, not to choose the right approach the first time. Like if you're not comfortable with that, you're going to, I think, really struggle in this class, because there's going to be a lot of times where you have to be comfortable experimenting and trying things. So I'm going to rewrite this again with my kind of color coding that I've been doing. So if we put the denominator is cosine of x, and then we have our dx. So if we let u equal cosine of x, then we get du dx is equal to, so the derivative of cosine is negative sine of x. Negative sine of x. And so if we multiply both sides by dx, we get negative sine of x dx. And so if we solve this for dx, we have du over negative sine of x is equal to dx. And so now we can go in and replace the cosine with u. And replace the dx with du times negative sine of x. So our sine of x's are going to cancel out, and so we're going to be left with the integral, and I'll actually bring this negative sign to the outside, right, because we have an extra negative sign there. So we have negative integral of 1 over u du. So we've successfully changed this into u's. So what's the antiderivative of 1 over u? Well, it's ln of absolute value. of u. Don't forget that absolute value. And then our last step is to go in and put back in our original function. So I'd really encourage you to try this with the other substitution. Try to just see what happens. See what happens if you try to let u equal sine of x. You'll see that things just don't work out the way that they did here. Okay, so next example I want to look at is the integral of x over the square root of 1 plus 4x squared. So I think this one is a little bit less obvious to kind of see what's going on, like what is our inside function, what's our, like what is the substitution to do. But again, what I would be looking for is look for something. So you want to be looking for two things. You want to be looking for, first of all, do I see the derivative of one of the parts of this function also in the function? And so here you might see, okay, well actually the derivative of 1 plus 4x squared is 8x. Right? And that's not exactly x, but it's only off by a factor of 8. And so as long as your derivative is only off by some constant multiple, that's okay. And then the other thing you want to think about is, if I were to make that substitution, would I be left with something I know how to take the derivative of? And you would, right? You would have 1 over the square root of u. And that's something you can rewrite using the power rule, and you can take the antiderivative. So let's rewrite this just with my colors, and then we'll get into it. So 1 plus 4x squared dx. Okay, so as we just said, let's let u equal 1 plus 4x squared. And so then du dx, and I forgot about my colors, du dx is going to be equal to 8x. And so if we multiply both sides by dx, we get du is equal to 8x dx. And so we're left with du over 8x is equal to dx. So when we put all of this in, we end up with x over the square root of u times du over 8x. And so this x here is going to cancel out, and we can bring that 1/8 to the outside of our integral, and we're going to be left with now 1 over the square root of u du. So another way of writing this, right, would be 1/8 times the integral of, so 1 over square root of u is the same thing as u to the negative 1/2. So when we take the antiderivative, we're going to, so we have this 1/8 we'll leave on the outside. Then we are going to add 1 to the exponent. So the new exponent is going to be positive 1/2. And then we need to take the reciprocal of that and multiply. So the reciprocal of 1/2 is 2 over 1. And then we have our plus c. And so if we simplify this, this is going to give us 1/4 u to the 1/2, or maybe we could rewrite that now as square root of u plus c. And that's the same thing as now we go back to our original function. So that's square root of, 1 plus 4x squared over 4 plus c. Okay, I think we'll just look at 2 more examples, but both of these are going to be examples that bring up something. Well, actually, one of them I think is just kind of a maybe slightly harder to recognize one, but this next one is actually going to bring up something that we haven't really seen yet. So let's say that we're trying to take the integral of x times the square root of x plus 1. So basically what's going on here is that, we you can't combine these, right? There's no way to kind of simplify this. And what we're going to do is we're going to do a U-substitution that at first might not seem that useful, but we'll see that will allow us to simplify the integrand in a way that we can actually then find its antiderivative. So I'm just going to kind of jump into it and tell you what substitution we're doing, but actually first let me write this. So basically what we're going to do is we're going to let u equal to x plus 1, and we'll see how that plays out in a second. So if we let u equal x plus 1, then we get du dx is just equal to 1. And so that means that du is equal to dx. So let's go in and make this change, and then we'll see that there's still something else going on that we're going to have to deal with. So we now have x times the square root of u times du. So we still have this x. How are we going to get rid of this x? Well, basically, think about this. You want to think of this substitution not just as kind of a one-time thing. Oh, this is just the substitution I'm making. This is a relationship between u and x. You can think of this as kind of your translation. You can think of this as your key for how do you go back and forth between u and x. So how do you go back and forth between u and x? Well, u is equal to x plus 1. And that means that x is equal to u minus 1, right? So we can rewrite this integral now as the integral of u minus 1 times the square root of u du. So you might look at this and say, like, we didn't really do much, right? We started with x times the square root of x plus 1, and we just kind of like shuffled things around. But this is actually now going to be something we can evaluate. And so the reason we can evaluate this is because we can now distribute. So we previously here, you cannot distribute this x because the x plus 1 is inside of a square root. But now the u minus 1 is not inside of a square root, so we can distribute. So we can rewrite this now as the integral of u times the square root of u minus 1 times the square root of u du. And this is something that we can actually take the antiderivative of because we can rewrite these using exponents and then use the power rule. So we have u to the 1 times u to the 1/2, so that is going to be u to the 3/2. And then we have square root of u, so that's u to the 1/2. And now we're ready to actually take the antiderivative. So the new exponent is going to be u to the, the new exponent will be 5/2, right? Because we add 1. And then we take the reciprocal of that, and that gives us 2/5. And then for the next part, we have the new exponent will be 3/2. And then we multiply that by 2/3. And then we have plus c. And so our last step is going to be to put back in our original input. So u was equal to x plus 1. So we're left with 2/5 times x plus 1 to the 5/2 minus 2/3 times x plus 1 to the 3/2 plus c. And then a slightly nicer way of writing this would be 2 times the square root of x plus 1 to the 5th over 5 minus 2 times the square root of x plus 1 to the 3rd over 3 plus c. But, I'm rewriting it this way because I think it, is a little nicer and a little more kind of similar to how the form that the problem was originally given to you in. But unless I specify, I would be okay, like on a test or something, if you left your answer like this. So, maybe I'll specify if I do want it written a certain way, but generally I would be okay with you leaving your answer like that. Okay, one more example I want to do. So last example is going to be the integral of the square root of ln of x over x dx. So again, this is going to be one of the more kind of typical ones where we're looking for something that we can substitute out to make the situation more simple. And additionally, we want the derivative of that thing to appear in our integrand. So ln of x is like the most kind of complicated part of this integrand, right? And so what's the derivative of ln of x? Well, it's 1 over x. And because we have divided by x, that means that we actually have 1 over x in our integrand. So we're going to be substituting out ln of x. And we'll see that the 1 over x part will get canceled out because of the derivative. So if we let u equal to ln of x, then we have du dx is equal to 1 over x. And so that means that du is equal to 1 over x dx. And so that means basically if you multiply both sides by x, that's the easiest way to get dx by itself, right? So that means that x times du is equal to dx. So now we can go and put that into our integrand. So we now have the square root of u over x times, and so what do we have here? We had x times du is what we're putting in instead of dx. And so this x and this x are going to cancel out. And so we're left with the integral of the square root of u du. And so that's something we know how to work with. So that's the same thing as u to the 1/2 du. And so that's going to give us u to the 3/2 is our new exponent times 2/3 plus c. And so our final step would be putting back in what our actual u was. So u is equal to ln of x. So we have 2/3 times ln of x to the 3/2 plus c. And so another way of writing this would be 2 times the square root of ln of x cubed over 3 plus c. All right, that is it. I know this was a long video. I know the last few have been long. That's not really my intention to make the video so long, but in this one, I just wanted to provide you with like plenty of examples so that you can see all the different ways that that substitution might be used. So again, I really recommend looking at the worksheet, trying some of these yourself, because it's one thing to see someone else tell you how to do it. It's quite another to be able to kind of see yourself what your substitution is going to be. And then, as I mentioned in tomorrow's video, we'll see how this works with definite integrals, and that video should be a lot shorter. So, we got, I think, most of the tricky stuff out in this video. All right, I will see you next time.